Thank you for joining me at Astrophotography Japan. I'm JP Astro Guy. My name is Paul. In the last episode, I showed you my planetary imaging setup and some images of Jupiter and Saturn that I collected last summer. Some of the feedback I received regarding that video motivated me to produce this episode to address some unanswered questions and terminology. Here in this video, I intend to show the impact of seeing conditions and video settings and how set point parameters and camera specifications interrelate, which can affect image resolution. Frankly, I did not fully appreciate this critical and simple fact of videography for planetary imaging until now, my fourth attempt at photographing Jupiter. I also generated some imaging data from my cooled deep sky camera and a planetary camera and have compared those results. So using the same Maxitoff OTA setup that I described in my prior video, I went out again for 2 consecutive nights to capture an image of Jupiter. Being now mid-January, Jupiter has climbed high in the night sky, allowing me to easily view and image it above the neighboring houses from my backyard. After an accurate polar alignment, I used a precisely aligned laser pointer as the first step and slewed to the target, which got me reasonably close and within the field of view of my eyepiece. Using a flip mirror diagonal to visually center the planet in the eyepiece FOV, I could next flip up the mirror and fine-tune the position of the planet's image on my camera sensor. Here is a ScreenCapture video image of Jupiter taken on my cooled color deep sky imaging camera, the 533 MC Pro. Notice the settings that I selected: a relatively high gain at 350, which is much higher than the usual unity gain setting of 105 that I typically use for imaging deep sky objects. This high gain allows me to set a very fast exposure rate of 6 milliseconds. These gain and exposure settings give an image that is slightly underexposed. Too bright is a problem, but dim images can be easily boosted in brightness in post-processing without any problems. Notice on the left, this image was taken at an ROI setting of 1080p. On this camera, that is the widest possible field of view setting, so Jupiter looks a bit small. Of course, you should always start with the widest FOV setting so that you can more easily find and center the target in your field of view at the start. Interestingly, the IMX533 sensor is 3008 by 3008 pixels, which itself is considered a smallish sensor with a 2.7x crop factor relative to full frame. But the 1080p setting is 1920 by 1080 pixels, even smaller. Now let's just focus on video imaging settings. The 1080p ROI setting is about 2.07 megapixels. Oh, by the way, ROI stands for region of interest. It is the activated part of the sensor where your image will be captured. It probably should be called ROA, or region of activation, but what do I know? There are several ROI levels for ZWO cameras. These include ROI settings of 1080, 960, 720, 480, 360, and 240p. The smaller the number, the smaller the field of view. For instance, on this slide, inside the 1080p box is shown the 480p sensor ROI. It occupies about 1/6 to 1/7 of the sensor area of the 1080p setting. So with this 480p setting, we are zooming in on the target, in the digital sense. But the number of pixels that a planet will cover on the sensor is exactly the same whether or not we select 1080p or 480p, right? So neither setting has an advantage over the other in terms of resolution, right? The size of the target, Jupiter, is the same in the projected image on the sensor, and the size of the pixels don't change either. So a digital zoom does nothing to improve image resolution. Well, that is indeed true, but there is more to this story, so hang in there. Now, on January 8th at 6 p.m., Jupiter was about 64 degrees altitude and looked like this in the Stellarium desktop application. If you look close, from the time it got dark until about 8 p.m., the red spot was moving across the planet and visible to us. So I was hopeful that I might be able to see it in my images. By the way, Jupiter rotates at the incredible speed of about 9 hours and 50 minutes to complete one Jovian day. Here is some video capture footage at 480p, showing a substantially larger image relative to the field of view. Notice here, the gain and exposure settings are exactly the same. This is going to be important in the comparison. So now let's look at the effects of first, the sensor ROI, and second, the seeing conditions on overall image resolution. On January 8th, between 6 and 8 p.m., the Air Transparency Index reported here on the MeteoBlue website was a mixed bag. Columns 1 and 2 under Index are two different assessment models for atmospheric transparency, or turbulence. The higher the value, with a maximum of 5, the better are the seeing conditions. Indices of 2 and 1 at 6 p.m. is bad seeing. 4 and 2 at 8 p.m. that night is good seeing. Another assessment value is arcsecond resolution, and as reported here, it varied from 1.94 to 1.66 during that time. These indices indicate that it was not a particularly good time to do planetary imaging, but I also knew that the next night would be better, so I proceeded with the imaging to have some comparative data and to practice my technique. Here are the best fully processed images that I could generate from Jupiter on that first night. The one on the left was taken at an ROI setting of 480p, and the one on the right taken at an ROI setting of 1080p. They are not bad, but also not particularly good. But they look different, don't they? Well, how could that be? They were only separated by a few minutes of time when I imaged them, and they used exactly the same menu input settings, video timing, exposure settings, gain, etc. They used the same sensor and telescope, and pretty much identical processing. How could one be so different than the other? Well, we already concluded in our previous discussion that ROI was just a digital zoom, and it could not affect the resolution. Or could it? Well, here is the answer as to why. Let me play for you the two screen capture videos from the ASIR video menu and display them side by side. The 480p capture is on the left and the 1080p capture is on the right. Look close at the numerical data. Do you see the difference? Look at the AVI frame capture rate at the bottom of the screen for each video. What do you see? Here is a random freeze frame showing the real-time image data and the settings from the ASIR menu display. Trust me, both image capture events have these identical settings. Yet one ROI, the 480p video capture rate, has a value that is about 6.8 times higher than the other. Gee, let me think. Where did we see that number before? So, what is this telling us? It suggests that there is a video frame rate limitation somewhere in the execution, computation, or data communication. For instance, 1080p never exceeded 10 frames per second. That could be interpreted as an exposure of 100 milliseconds each per frame, or a 6 millisecond frame that takes 100 milliseconds to transfer it. Certainly I set the exposure properly, and clearly the camera has the capability to execute a 6 millisecond exposure. So the most likely explanation is that the sensor readout appears to be limited in the number of gigabits per second for data transfer. And there is some other evidence to support this conclusion, but I won't elaborate here. If we look at frames per second rate of the 480p video in real time, it averages around 50 frames per second. This is because the data file is approximately 7 times smaller at this ROI setting, so many more files can be sent per second. The only way to know your true frame rate transfer in real time is to watch it on the menu where it says AVI frames per second. Now is it clear? The reason why the 480p setting gives a better image than the 1080p is because the number of image frames in the captured video is much greater. At both ROI settings, an exposure time of 6 milliseconds is being executed by the camera firmware, but the frame rate, the number of frames per second being read out, is being limited by the image file size. The smaller FOV settings like 480p have less data per frame, and consequently transfer speed is proportionately faster. You end up with way more image frames in the video file for the 480p setting, and this helps the processing software to generate a more clear and clean image. Let's look at this one more time on a second night of imaging. The very next night, January 9th, appeared to have much better seeing conditions. Notice from 6 p.m. to 8 p.m. the indices were higher and the arc seconds were lower, and it was rather stable or consistent from hour to hour. On this night, Jupiter crossed the meridian at 6:43 p.m. and I captured all my data between 6 and 7 p.m. when Jupiter was highest in the sky. No red spot would be visible from Earth on this night, unfortunately. And obviously, we did not really resolve it on the previous night's images either, due to or partially due to the less favorable seeing conditions. Here is how the images looked on night 2. Shown again is a comparison of ROI settings at 480p and 1080p. We see the same effect. The 480p setting image is slightly higher resolution. And by the way, I did not mention this earlier, but I am using the AstroSurface software to process my planetary video images. I just discovered this powerful free software and the results are fantastic. I will say a bit more about it later. Another thing to notice is that the quality of the night 2 photos are better than the quality of the night 1 photos. Shown here is a comparison of the meteorological data and the best 480p images taken on those nights. You can see that the settings are nearly identical except for the imaging time. Night 1 on the right is a 3-minute capture, and night 2 on the left is a 4-minute capture. And don't read too much into this. That really does not make much difference at all. It is mostly the sky conditions that explain the differential results. I realized on the second night that there is a limit to the length of time that the ASI is willing to capture video data. That limit is somewhere between 4 and 5 minutes per recording, not because of the time, but rather because of the file data size. If I recall, based on my experience, there is a maximum allowable 4 gigabytes of video file data size. If you exceed that file size during the recording, it automatically terminates the recording. When I learned this information, I tried to push the limit further on night 2. But I am not so sure now that was a good idea. For fun, I did a little measurement and calculation. At this focal length and on the IMX533 sensor, the image of Jupiter occupies just under 100 pixels across the equator or the width of the planet's image. Yes, I counted them. Remember earlier, I said that Jupiter has a Jovian day of about 10 hours. Well, it is exactly 590 minutes. And if we assume we can see 50% of that from our viewpoint, which is an overestimate by the way, but let's assume that, then an object like the Great Red Spot will transverse across the face in about 295 minutes. So if we have 93 pixels covering the width of the image, each pixel represents about 3.2 minutes of rotational distance. If we created one stacked photographic image from more than 3.2 minutes of video data, we have allowed some data to move across the boundary of one pixel onto the next during that time. This can and probably will create some blurring. So if you image too long, you are artificially reducing your potential resolution. I am going to guess that perhaps only a minute or two, or thereabouts, is the best capture time for this optical tube assembly. Oh, by the way, I recognize that the blurring effect will be greatest at the midpoint of the image where, from our viewpoint, the speed of the horizontal movement appears fastest. As you move away from the center point, the movement is slower from our viewpoint because we are capturing 2D data from a 3D sphere. Hopefully you can visualize it from my description. Think about it. Finally, I also captured image data using two different cameras on these two nights. The ASI 533MC Pro camera is what I routinely use for imaging of deep sky objects, and the ASI 678MC Planetary camera is what I purposely bought for imaging planets. Both have 0 amp glow and both are fairly new ZWO camera models. Here are the ASI 533 images at both ROI settings. And again, the 480p image looks better. Here are the ASI 678 images at both ROI settings. Again, the 480p image looks better. And here's a comparison of the best 480p images from each camera. Also displayed are the key specifications. The settings are very close, but not identical. That is because they are different cameras with different sensors, and they respond differently to light conditions. So I optimized the settings for each independently. But they are very close. For instance, both are at gain 350. Oh, I know what you're thinking. But no, the image quality difference is definitely not due to focus. Each camera was first precisely focused using a batten-off mask on the star Alpha-Rats prior to any video capture. And I saw this same difference when I inspected the images taken on night 1 with both cameras and images taken on night 2 with both cameras. It is definitely not a focus problem. For my eyes, I think the IMX533 sensor in the ASI 533MC Pro color camera did a better job of capturing a better image. I am not sure if the resolution is any higher, but certainly the depth of the color and the contrast are much better, and it was easier to process after stacking. Frankly, this is not what I expected, and I find it to be a little disappointing. I guess maybe I did not need to buy that Planetary camera after all. As I mentioned before in the prior video, the pixel size is much smaller on the 678MC Planetary camera, which theoretically could be an advantage. And the frame rate could be much faster at highly cropped ROI settings. But the full well depth is quite shallow, and the analog to digital converter value is also much less than the IMX533 sensor, so the color range is less. But I really do not know why the 533MC Pro camera seems to be consistently working better for me at planetary imaging. This is not the first time I noticed it. It may be that all of these specifications together simply are superior or better suited for my OTA setup and the typical sky conditions I experience here in Yokohama. I really don't know. Oh, by the way, I did push the 678MC camera to an even higher digital zoom ROI setting on night 2 for fun. This is the image taken at the 240p ROI setting. Notice how big the planet looks inside the FOV. This image is not cropped. And here are the images of 1080, 480, and 240p all side by side. These are all images from the 678MC Planetary camera. The last one at 240p may actually be the best, but they all seem to lack contrast and color depth compared to the results from the other 533MC camera. However, I wanted to make another point on this slide. Notice the table showing the video time, file size, and number of frames. Even though the 240p image was only 90 seconds long, the number of frames is staggering. I also suspect something else based on this chart. That is that the file size is rather consistent regardless of the ROI setting. Both 4-minute videos taken at 1080p and 480p are about the same file size. This is despite there being at least 5 to 7 times as many frames in the 480p video taken during those 4 minutes. And I suspect that if I took a 4-minute video at 240p as well, it also would have ended up with a similar file size at around 3 to 4 gigabytes. Interesting. Now let me give you a plug for a new ZWO camera, the ASI 664MC Planetary camera. This was just recently released by ZWO, and it has caught my eye. In comparison to the 678MC camera, it has a much deeper full well depth, higher frames per second, and substantially higher efficiency. Its read noise is lower, and its pixel size is a bit bigger, and the sensor is basically the same size. I am thinking the performance of this new camera will definitely improve on the 678MC results that I have been getting. But do I really want to spend another $300 on another ASI camera again? Oh, by the way, Uranus was in the sky nearby to Jupiter on those 2 nights as well, so I took some video of it too. Of course, at the 1365mm focal length of the Zwiebony MK105 telescope, it is impossible to see any surface details on this distant ice giant planet located nearly 2.9 billion kilometers away. But it was wonderful to see the natural blue color and globe shape come across in the final processed image. Perhaps you noticed that I used ASIstudio to process this image. That is because there was not enough pixel data on this tiny little planetary image for AstroSurface to recognize it. It just did not work. But ASIstudio did a decent job. I guess this video has really been about identifying some critical limiting factors on resolution in planetary imaging. I doubt that we covered all possible topics, but we talked specifically about these factors: seeing conditions, which are natural air disturbances, telescope specifications, we talked a lot about the rotation speed of Jupiter, and camera specs. And I also showed you that just because it is labeled a planetary camera, it does not mean it will give you better results in planetary imaging. And finally, I am a happy new user of the AstroSurface stacking and processing software. Among the options listed here, I definitely prefer and trust AstroSurface. Previously, I used ASIstudio, which I think a monkey could operate. It is that simple. This chart is a basic comparison. AstroSurface has built-in wavelet functions and many more image processing and analytical capabilities. You should check it out. This slide shows a side-by-side comparison of the recent images I processed, to the best of my abilities, using both software. Of course, I know none of these pictures shown in this video are going to win any awards, but I am inspired to chase better and better results with the equipment that I own, rather than investing more into the endless equipment money pit we call astrophotography. Each step forward inspires me to try something else, like perhaps capturing the Great Red Spot, or photographing a Jovian moon transit, or moon shadows, or creating a rotation video, or just improving on my best planet photo. There are so many options. Well, that's all I have for this rather long video. If you stuck around to this point, thank you very much. I hope you picked up some tidbit of useful information, and I appreciate your interest in Astrophotography Japan. I am JP Astro Guy. My name is Paul Cheesegel, and I
am an astrophotographer.